Hello and welcome to this SCX platform update. We will talk about hardware only, SCX7K, that's a Jericho 2 based platform. What we do have today on the portfolio is the following: an SCX7100 32C, another version 48L, that's the 1RU boxes with 4.8 terabit per second of forwarding capability. We do have the SCX7509, 5RU high, control plane and forwarding plane redundancy, and 3 different type of FPCs. And we also have the SCX7024, which is Ultron, the smallest platform today for aggregation from SFP to 100 gig. We're going to introduce the SCX7348, the first one on the 73 series. We will have the SCX7024X, a new version of the Ultron. We're going to have the SCX7332, offering slightly less number of ports, but higher scale with the addition of an external eTCAM on the side of the PFE. And later on, in the second part of the year, we're going to have the SCX7020, the Ant-Man. What we could do for such a presentation is to go over the platforms one by one and list their port density and specifications and scale and what they can do, cannot do. Or we can try something with a slightly different angle, which is explaining how and why we are designing the platforms the way we do. What is the thought process behind every selection, every decision? We picked that particular PHY, that particular chipset, or selected this form factor for X, Y, Z reason, basically to put yourself on the shoes of a PLM. And we'll start with hardware, the form factor. This is the SCX7100 32C. You can see 32C QSFP cages on the bottom, plus 4 ports QSFP DD, 56 for 400 gig. On the top, we have the fan modules, 6 blocks. On the side, the PSU, 2 power supply with air baffles. Everything in the center, represented in grid, is one big PCB, which is the main board, the motherboard. We have on the center a big heatsink, which is covering the PFE. The heatsink is usually twice the size of the PFE, sometimes more. Also, we have another one here covering the CPU and the SODIMM DRAM, the memory used with the CPU. All of them are installed on a daughter board, the CPU board. And talking about boards, we have another daughter board on the top, the fans board. This one is connected to every fan modules and also to the motherboard and decide the speed of each fan. On the bottom, between the PFE and the optical cages, we have a line of heatsinks covering retimers, what we call FI. So we will see why we have them and what type of role they occupy in our design. Sometimes also we will find other parts like the PTP FPGA that we have on the right of the PFE. And you will need a MUX, a TI MUX, to interconnect it to the PFE or to connect the PFE to the revenue port. So all of this you can see on the right is really occupying a lot of space on the board. We don't have much room. And if we wanted to shorten the size of the chassis and particularly the depth of the chassis, we don't have that many options. We need to play with multiple parameters. It will be the number of components. We can decide to have less. We can use smaller components, or we can decide that certain parts cannot be replaceable, so we can make them fixed. And finally, we can play with the number of rack units. That's the case of this new platform, the SCX7300, that we're going to launch in December and January. This page is just showing you in a very synthetic manner the different form factors that we have on our current portfolio. Every router I was listing before are offering fan tray and power supply redundancy. We have also other type of redundancy, which will be on the control plane and the forwarding plane. And the only one offering both will be the SCX7509. The 7300, on the other hand, will offer just control plane redundancy. So the first one, 7509, is a 5RU system, still centralized in the sense that we don't have 6 fabricants, we just have 2 of them, we call them FIB. Then they are acting in active standby mode, 1+1 mode. We are showing a side view here where we can see the FIB are between the FPCs and the fan trays. We can populate the system with 8 different FPCs and they will be interconnected to a mid-plane through connectors. And you will see in a few minutes what are the implications of having these connectors in terms of signal integrity. Mid-plane means we're going to need to have very strong fan trays to guarantee we have proper cooling and we maintain the right temperature everywhere. That's something we optimized significantly, introducing the 7300. Now we don't have a mid-plane anymore. So that authorized very differentiated design where we would have, of course, shallow depth of field, but also the iTemp capability that is unique to that form factor. This ACX7300 is a free RU system, again, mix of fixed ports and modular ports with two RCB routing engines, but a single chipset internally, which is a Jericho 2C. So it's a centralized system with control plane redundancy. So talking about cooling, there is three big categories. If you put aside the water cooling and the fanless systems, we have front to back to front, and side to side. In the SCX7K portfolio, all the routers are front to back. One is back to front also, which is the SCX7100 and another one will be side to side. That will be the 7020 that is under preparation for 2024. Cooling and also more generally the thermal design optimization of a router is a very critical part. That sometimes implied to change some initial plans. So that was the case for this 48L, where initially the ports were positioned slightly differently. We decided to move the 6-port 400 gig in the center to guarantee that we can operate well in back-front mode. And also you understand why we cannot get high power optics with this approach, because of course the optics will be the last one being cooled by the air going through the product. Also, when we talk about cooling, we need to differentiate products where we have fixed parts and modular parts. Basically, the only fixed part will be the SCX7024 and 24X systems. We are doing that for economical reason, but also for the footprint. It's going to occupy less space. All other systems will offer modularity, and we have N+1 type of redundancy. Another decision we are making when we are designing the product is the selection of the optical cages. There is basically two options, using belly-to-belly or stacked cage. Stacked means two rows in one single cage with basically only the top row in contact with the heatsink. That means the bottom row is not as well cooled as the others. With such an approach, it's difficult to have high power optics on the bottom. We are avoiding that situation by using just one row cages. Each of them is directly using the heatsink, and we are positioning them in sandwich mode. That means the top rows will be above the PCB and the bottom row will be attached on the bottom. That way we are providing an optimal cooling capability, particularly with the new optimized ZR optics coming in 2024 that will consume quite a lot of power. It's common to talk about iTemp, cTemp, a bit less eTemp, but you need to understand that these concepts are very component, but also industry specific. What is less subjective is the standards like ETC classes and NEBS, GR63 and 3108 standards that are very precisely defining the test and what it needs to be supported in terms of environmental conditions. The products can be sorted in three big categories. On the iTemp industrial side, you do have the 7020, the 7024, and the SCX7348. So you can operate in a very large range of temperature. On the commercial temps category, you will have the SCX7509, the two SCX7100, and the 7024X. We'll explain you in a few seconds why this one is not iTemp. And there is something in between, the SCX7332, which is more capable than commercial, because of one part, the external eTCAM OP2, so we call it eTemp for extended. Let's talk about the engine of our routers, the PFE options. And for this selection process, we will need to use multiple parameters to decide which one of the 35 different SKUs offered by Broadcom is the most optimized and suitable chip. We'll have, of course, bandwidth, the number of SerDes links or lanes we want to have, the types and the speed we can operate them, the number of queues, the number of counters, the size of the memory, whether or not we do need to interconnect them through the fabric side. Will they need to be industrial temp or just commercial temp? The size of this chipset and how big should be the heatsink to cool it down, the power usage, and finally the cost. Let's go over all these aspects one by one. Basically, in our current SCX7K portfolio, we are using 4 different types of chipset. The Jericho 2, the Jericho 2C or Qumran 2C, the Qumran 2U and the Qumran 2N. When I talk about Jericho and Qumran, in principle, with Jericho, you can interconnect to a fabric card or directly in back-to-back mode to another PFE. On the Qumran 2, you are not using any kind of fabric SerDes, and basically it's a system on a chip where all the one SerDes are connected. So that's the high-level definition, which is good for what we need to do. If we want to have a closer look to the Jericho 2, we can represent it like this. 2 cores, 0 and 1, each one of them capable of 2.4 terabits per second of forwarding capability, full duplex, 1 billion packets per second. So that makes it 2 billion, 4.8 tera total. We have 48 links on the one side that can be operated up to 50 gigabit per second. And slightly more on the other side with twice 56 fabric links. They cannot do any kind of MACsec internally, and they can deliver Class B timing quality. We are using them on the ACX7000 and the 48L. Now, the second chipset I'm showing here is a Qumran 2C or Jericho 2C. At high level, I will say it is half of a Jericho 2 with a single core, 2.4 tera of forwarding. What is different is the number of SerDes and their category. I will come back on that in a second. We're going to have half of the memory, external memory. And for the rest, it's very similar, Class B timing, no MACsec. We're going to use it in the two ACX7300, 32 and 48, and on the FIBs inside the ACX7509. The Qumran 2U, we're going to have something significantly smaller. Here, we don't use any more NHBM. We are going to use an external graphical memory of 2 gigabytes. We have 40 links up to 25 gigabit per second, and it can push a total of 360 gigabit per second. It can do Class C instead of Class B compared to the other, but still no MACsec. And we have this chip in the SCX7024 and 7024X. Finally, the smallest one in our portfolio is a Qumran 2N. This is a 100 gigabits per second chipset of single core with 20 links up to 25 gig. And that is using also an external graphical memory, GDDR6 of 1 gigabyte. If you compare with these diagrams a different type of bandwidth, you can see both PPS and gigabits per second. So you can see there is a large variation between biggest one and the smallest one. Also very interesting to note that the Jericho 2 that we have on the right is not oversubscribed. That means we can push 4.8 tera. Things that is slightly different on the other category, starting from the Jericho 2C, that is capable of 2.4 tera, but you can connect up to 4 tera of bandwidth of links to it. So it's by design oversubscribed. So Qumran 2U also can have 360 gigabits of forwarding, while you can interconnect 1 tera of interfaces. Likewise, on the Qumran 2N, you have 100 gig of forwarding, or while you can connect 500 gigabits of interfaces. These products are purposefully oversubscribed. They offer more interfaces, more links than they can actually forward. And when we talk about links, we talk about SerDes. This is a key concept to understand what type of interface we can provide. First of all, the SerDes is a component. It's required to interconnect to the rest of the chassis or the router, and this element is actually something we buy from third-party vendors. Broadcom is offering their own SerDes, and depending on the maximum speed or the speed you run these links, you will be capable to provide different type of interface. For example, if you consider 100 gigabit Ethernet, SR4 or LR4, ER4, so what you have is 4 links of 26.56 gigabits per second, where the information is encoded in non-return to 0. I will simplify by saying 25 gig, 50 gig, 100 gig, but in reality, you can see those numbers are in reality 26, 53, 106. If I want to create, let's say, 400 gigabit Ethernet, I will need 8 links at 53. That's my 400 GAUI8. If I want to offer 800 gigabit Ethernet, that means I will need to have 8 SerDes at 106 gigabit per second. The one SerDes offered by Broadcom are called PM25, port macro 25, and PM50. The PM25 can give you 4 SerDes that you can operate from 1 to 25 gigabit per second. So you can use it for 1, 10, 25 gigabit Ethernet with 1 SerDes, up to 100 gigabit Ethernet with 4 SerDes at 25 gig. The PM50 is offering 8 SerDes that you can operate from 10 up to 50, 53. That means you can use it for 1 time 10 gig up to 400 gig, 8 times 50. So you understand something directly with this chart. On the systems based on Qumran to N, the 7020, or the system based on Qumran to U, the 7024 and 24X, you will not get 400 gig because you need 50 gigabits per second SerDes. That is not an option on these systems. Likewise, on Jericho 2, you will not get natively 1 gigabit Ethernet. There is still ways to do that through an intermediate device, but natively, you cannot operate this SerDes at 1 gigabit per second for 1 gig port. So you can see that Jericho 2C and Qumran 2C we use on the 7509 and 7300 is offering a mix of PM25 and PM50. That means we have the capability of having a larger span of interfaces with this, but with some constraints in the position, because the mapping is done statically when you boot up the system. So now let's illustrate it with the ACX7024. On the center, we have 4 ports, P0 to P3 at 100 gig. Each 100 gig is, again, 4 SerDes at 25. 4 by 4 equals 16. Then you have the port 4 to port 27. Those are the 24 ports SFP. SFP means 1 single SerDes. So you do the math, 16 plus 24 equals 40. If you take a look again at the Qumran to U, that's exactly what we can accommodate. So you understand that the port density of an ACX7024 is directly derived from the number of SerDes we have on the Qumran to U. In certain products, we have Jericho 2, and some other times we have 2 Jericho 2C in back-to-back. And that's what we have on the SCX7100 32C and 48L with only a single Jericho, and the SCX7509 FIB with 2 Jericho 2C back-to-back. So why do you do such a thing? The benefits are simple. Number one, with Jericho 2C in back-to-back, we have a mix of PM25 and PM50, offering natively a larger span of interface options, from 1 gigabit Ethernet to 400 gigabit Ethernet. That's very good for the aggregation device we try to build. Second, we can oversubscribe the Jericho 2C, which is not supported on Jericho 2, 4.8, that's it. Here, with this oversubscription, we can have potentially up to 8 terabits per second of interfaces. Also, and that's not negligible, we have twice the number of queues and the number of counters on Jericho 2C. But when we do that, we have to accept a larger footprint on the board, and also we're going to have to interconnect those 2 PFEs with fabric SerDes, and we're going to consume more power in the process. So that's a drawback that we accept to get more flexibility or interfaces, and that's something we don't do on the SCX7100. Now let's talk about another very important component in our routers, the PHY. PHY, gearbox, river gearbox, retimers. Let's explain what it is. In this example, I'm representing a PFE connected to the same PHY, but programmed in 3 different modes. On the top right, I do have the forward gearbox. What it does is on the host side, it is connected to, let's say, PM25 with 25 gigabits per second SerDes, 16 of them. And on the line side, it will convert that to 8 SerDes at 53 gigabits per second. On the left, it will encode it in NRZ. On the right, in PAM4. On the bottom right, the reverse gearbox mode will convert a certain amount of links at 50 gig in twice that number in 25 gigabit per second mode. So it does what we call fan out. So we have 8 by 50 on the host side. Now we have 16 by 25 on the line side. That way, we can accommodate 4 ports, 100 gigabit Ethernet. On the left, this PHY is configured as a retimer, where the host side and line side are having SerDes at the same speed and same encoding, but it will be reamplified and realigned. So we do that for certain situation when the signal needs to be boosted because of long distance, because of attenuation, because of multiple reasons that make the signal not as good as we want to reach the interfaces. Behind each PM50, we will have a budget of 8 MAC addresses. If we are using 4 ports 100 gigabit Ethernet, that's fine. We are using 4 MAC addresses out of these 8. Now, imagine that we decide that each of these 100 gigabit Ethernet needs to be channelized using a breakout cable that will give us 16 interfaces, and we have only 8 MAC addresses in our budget. That's why it's very common to see that when you configure channelized on the port number N, the port N+1 needs to be configured unused. That's something very common. And that's what we're going to illustrate with the port checker tool here. In my port number 2, I have 4 times 25 gig, and my port number 3, N+1, needs to be configured unused. On the router itself, if you don't configure unused, it will not even complain that you are doing something wrong. It will simply not enable your channelized port. That's something good to know. The PHY transceivers can be configured in retimer mode, and that's something you will see typically when you need to reamplify the signal, whether it's a very long trace on the PCB, or if you do have modular parts, the FPC, that you're going to insert on the ACX7009 and ACX7300 will be connected through connectors, and this will have an impact on the quality of the signal. So that's why every FPC is always coming with a retimer to reamplify these signals and give it a better quality. But modifying the SerDes speed and encoding and improving the signal quality are not the only reason we are using these PHYs, because they are coming with interesting additional features like timing and MACsec. And if you remember the PFEs we listed, none of them does support MACsec internally. So we're going to have to rely on these components to provide this type of services. That's what I'm showing in this example, the ACX7132C. So the PHY are used in gearbox mode in all 100 gig ports. And also you can see that we have a couple of them on the right between the PFE and the 400 gig ports. And you can ask yourself, why do we need to do that? Because we do need 50 gig SerDes on the interface, and that's exactly what the PM50 are giving us. But the PHY configured in retimer mode here will be only to provide MACsec services on these 400 gigabit Ethernet ports. Other example, with the 48L, we are showing that we have no PHY present between the PFE and the optical cages. Therefore, we cannot provide MACsec services. What about the other components that we do have on the router? For example, the CPU. We have 2 big categories of CPU, the C and D class from Intel. It's interesting to note that when we are building far-end systems, that means small form factor with very optimized cost. That's why the SCX7024 is shipping with a CPU with 4 cores at 1.6 gigahertz and only 16 gigabyte memory, which is absolutely fine for this aggregation use case. But if anyone would like to use this SCX7024 for enterprise role, they will very quickly hit the limitation of the CPU before reaching the maximum scale of the PFE. That's the reason why some people ask for a different version of this product with the same port density, same forwarding capability and features, but with a stronger and more powerful CPU and larger DRAM space. We have this ACX7024X exactly to meet that requirement, with a CPU made of offering 8 cores at 2.9 gigahertz and 64 gigabytes of RAM. The consequence is this type of chip and memory are not iTemp. That's why this product is no longer in the industrial temp category, but on the commercial side. The ACX7000 is really strong on timing. That's a very big differentiator compared to the competition. We have 2 main hardware parts that are making this. Number one, the GNSS antenna receiver that we have on the SCX7300, On the other products, we can still rely on an external part, the TB1, that can be connected with, via the USB and timing ports. It's what we call a reference cell. That means we do have the software support for it. The second differentiator is the PTP FPGA that we have on all 7,000 products. That is something we are building ourselves. It gives us very high scale, number of peers, and Class D quality. And also with the choice of PHY, we are guaranteeing PTP over MACsec. So when we configure the PTP features, we're going to have to disable a revenue port. And that's what I'm illustrating here with the port checker on the ACX7024. So specifically on the SCX7332, we have an additional part called OP2, an eTCAM that will come completing the PFE. We will have higher FIB, even if it's no longer such an important thing, and we will see why in a few seconds. But it will give us much larger number of firewall filters and statistics. That will open the door to certain use cases that were not always well addressed by this type of products, particularly on the peering side, the enterprise, and the distributed BNG, the BNG cups. This diagram illustrates why we have a slightly less number of fixed ports, because we need to interconnect this OP2 part via SerDes. That's what I'm showing in this picture, in this diagram. Another very important dimension in your selection process for PFE is the memory size. And when we talk about memory, basically on DNX, we mean MDB, modular database. This MDB is carved at the boot up into multiple memory blocks that will be used for everything that you need to store, from interface, routing, next stop on caps, translation, tunnel termination, VLAN manipulation. Everything that you need to do is spread among these different memories. That includes your route v4, v6, and PLS MAC addresses. So these routes, we are going to change the way we are sorting them, and that's done in 23.2. Before that version, we used to have MAC addresses, MPLS label, and host routes, v4 and v6, positioned into LEM, large exact match. And the rest of the routes were pushed into LPM, longest prefix match memory. Starting from 23.2, we are simplifying the things with all the routes, host or non-host, v4 and v6 going to LPM, and only MPLS labels and MAC addresses are stored in LEM. Just for information, we consider that an IPv6, in average, an IPv6 route is twice the size of an IPv4 entry. That is something that you can verify on internet. The MDB comes in two sizes, and depending on the chipset, you will have on the Q2U and Q2N an MDB of 1.5 million entries, and on the other chipsets, the J2 and Q2C that we are using, it will be a 3 million entry large MDB. And what I'm showing here is the different distribution, and we call them profiles. And it's a very good way to specialize the routers in a given role. When you want to be more L2 specialized or more L3 specialized, you can decide to allocate different sizes for LEM, LPM, etc. We are also going to change the way it is working significantly starting from 23.3. Remember, shipping in 23.4. These profiles existed from previous version. We used to call them L3XL, balanced L2XL, and balanced eTCAM. We are renaming them to now the role we want to occupy, so Lineage, Cloud Metro, Carrier Ethernet, and BNG. And we are modifying the default mode. So it used to be balanced. Now by default, it will boot in Lineage if you don't configure anything, simply because the majority of our customers are using the product as L3 routers. Also very important to note that with the numbers we are showing here are not representing supported scale, just the memory. We could have other bottlenecks that will not let you push the envelope as far as those numbers. But it's a very good way of understanding what does what and see the different proportions that we have. Another important differentiation is the merging of private and public domains. So that's something you may have seen in previous version. You needed to define from the get-go how many routes you expected to come from the global routing table or the VPN tables. private for VPN, global routing table for public. And this carving needed to be done when you started the system. We didn't have to do it with balanced, but all other profiles like L3XL and L2XL were based on that logic. It could lead you to a situation where you had eventually less number of routes in your L3XL if you want them in the global routing table compared to your balance mode, which was a bit absurd. So all this complexity has been eliminated. You don't have to care where the routes will go. We have merged private and public. So this is now done, and all this, it will completely disappear from the CLI. You don't have to worry about that anymore. And talking about routes, it's important to mention that we are introducing some very cool feature inherited from the PTX Express 4 platforms. It's coming in 23.2 R1, and that's the FIB compression. It will be enabled by default on all products, with the exception of the ACX7024. So if you are interested in more details, you can go to that blog and watch the video. We are explaining the way it is working on PTX. Just to explain the way it works. Number one, if you have a covering prefix pointing to the same next stop than a more specific prefix, that's the example I'm showing here with 2.2.4/30 and pointing to NH1, and we have 2.6/31 pointing also to NH1. This one does not bring any additional information. We can live without it, therefore we will not program it in FIB. That's the number one rule. The second is simply a summarization. If you do have subsequent prefixes like these 4 host routes from .12 to .15, we will only program the summarized version of that, which is an aggregate, and that can be cascaded up to the highest possible place where we're going to have all these routes covered. And that will be in our example, the .12/30 pointing to NH1. Again, very important that everyone is pointing to the same next stop. And next stop here is only from the perspective of the FIB. We don't care about the protocol who did advertise it. It could be BGP, ISIS, OSPF, static, or directly connected. It's really from the FIB perspective. So another rule to understand is we can aggregate routes at different level of the tree. And in this example, I'm showing 4 subsequent routes/31 pointing to the same NH1 and a more specific /32 routes pointing to NH2. That means I will have 2 routes programmed in my FIB by /29, that is the aggregate of this guy pointing to NH1, and this one, .5, pointing to NH2. Simply because of the longest prefix match rule, this one will be matched first. If there is no match, it will land in this level. So this is simple, but it's very, very efficient. And we can illustrate it very simply with this example of 12 different routes, /31 and /32, all pointing to NH1. You can see that the first level of the tree at /32 is creating aggregated that themselves will be summarized with other advertised routes and on up to our /28 NH1. If there is multiple next stop, of course, we'll go as far as the summarization allows. That means this couple of routes here, just 3 entries, 2 pointing to NH1, another one pointing to NH2. So you understand that the only important parameter is the distribution of your next stop. In this last example, if I do have my summarized route /28 pointing to NH1, and it happened that one of the contributing route disappears, it will break the tree into multiple branches. And likewise, if I receive a new route with a different next stop, we're going to have this structure programmed in the FIB. From an implementation perspective, everything is happening at the very last moment. Inside the Evo PFE MND process, we have this block called Broadcom Async, and this is where we're going to apply all the logic of the compression. So that means it will have no impact on your RPD, FIBD, and however we're going to distribute the routes between processes. It will not impact your redistribution, the route leaking, or anything. It will be fully transparent from a control plane perspective. It is only a local decision happening at the very last moment when we program the route inside the hardware. Also, in terms of performance, we measured how it's behaving. In this example in the lab, we collected routes from a real router, But with only a single neck stop V4 and a single neck stop V6, that is basically the best possible case, because if you have just one neck stop, we can see how far we can compress the internet. And what we have seen is a 82% compression for V4 and 72% for V6, which is quite impressive, at least on the V6 side. I was expecting routes to be more scattered, considering the very large addressable space. But that gives you the best case of how far you can go compressing the real internet table. A very common question is the impact on convergence and programming speed, and we did the measurement with or without the function because we have this hidden command to disable it, and we are seeing no difference in terms of programming speed. That means 22,000 prefixes per second. Again, we don't do that on the ACX7024, so that's the only place where it will not be activated by default. I will invite you to check all the blogs that we are posting on TechPost. You go to juniper.net/techpost for your weekly dose of technical content on our products. I strongly invite you to take a look at that. There is a lot of good content with a lot of talented writers. And in case of doubt, don't hesitate to check the Pathfinder tools like the HCT, the hardware compatibility tool, the port checker, or the power calculator. They are valuable resources. Okay, that's all for me. Thanks for your time, and see you in the next one.